until you start to talk to folks, and then you understand, oh, I can look at the source, and I can see the comments that have been made over the last 25 years over why the nested loop join prefers this kind of thing when it does this, and like, oh, there's a lot there. And so that uniqueness, you start to pick up some of the nuances of how you can affect some of this. So for this, at least as a first pass, and this will evolve over the next few times I do this, we're going to focus just on query plans, which you've all seen, but just making sure we're understanding the pieces of it. And then just nuances of some configuration and tuning, and hopefully a couple of demos, just, hey, here's a couple of switches that you can tune, and just see what might happen on the other side of it. And we'll go from there. So this is who I am. I am part of Redgate, and I've been there just now past 2 years. You can contact me, Ryan Booz, at these 4 places or 3 places, and then my blog. I don't do other socials for the most part, so I might be there, but I'll never answer you. It's not because I don't think you're a great person. I just am not there. All right, so I'm just going to dive right in and talk about, obviously, performance tuning and how do we even go down this path of performance tuning. And at the end of the day, again, particularly if you have come from another database, Postgres is still, as most relational databases are, still purely a cost-based optimizer, right? So when you type your SQL query, under the covers, the parser parses that query, and it says, hey, I have a way to determine based on statistics what I believe is going to be the best plan. So the way a cost-based planner works is it actually is trying a lot of different possibilities very, very, very quickly, and it makes a choice as quickly as it can of what it believes is the cheapest yet best possible plan, right? There might be, if we let it go for 2 or 3 seconds, it might find the absolute best optimal plan, but we don't want query planning to take 2 or 3 seconds. We want it to take 10 milliseconds. And so it does its very best to say, hey, I tried 3, and this one costs less. We're going to do that. And like, I wish you wouldn't have chosen a loop join. Like, how could we do something else? And so you can customize statistics per server, which is actually the cluster. So you can say at the cluster level, statistics by default, which is on probably the next slide, it is on the next slide, is 100. So when we talk about statistics, it looks at every column, and it says, hey, I'm going to build a histogram on the contents of this column. And so a histogram is a number of buckets, right? So it's a beginning value, ending value, and it decides how do I evenly divide this up so I can kind of have a clue in this bucket, there's this many values in this bucket, so what's the range in between? And then it does some other things. So Postgres keeps a couple other statistics, like most common value. So for every column, it will actually, when you look at PG underscore statistics, it's on the next slide. It's on the next slide. PG stats and PG stat user tables. PG stat will show you these things. And so most common value, and there's a couple others. All of those feed into the query optimizer, right? It has to understand the relationship. If it thinks it's going to get 1 billion rows on one side of a join, it's going to do everything it can, hopefully, to choose something other than a nested loop, because otherwise you don't want to loop over 1 billion rows, right? And so, anything else here? Sorry, and then you can set it on the table and the column. So usually the column, yes? Yeah. But if they're not run, then you're going to have all the pages on one line. And the rest that's good. That's great. That was the best analogy I've ever had for SQL. Very good. Yeah, I'm not sure you're a better guy. No, I appreciate that. I've honestly, you talk about even something like histogram, it's like, man, I'll take that. That's a good one. So it's maintained asynchronously. It should be. So since Postgres 9 point whatever, the automated auto vacuum, auto analyze runs on a percentage basis, right? So the biggest thing, and so this was one of the things I learned yesterday listening to Bruce give his talk about the optimizer, is these things are configurable in a lot of other databases or not. So if I know his point was this: 100 buckets work surprisingly well for all kinds of data distributions. The fact that I can tune it to be something different. So let's say I know I have a significant number of unique values in this column in a distribution that it would be helpful for the planner to say, hey, I want to divide that up not in 100 buckets, but 200 buckets, because that gives me a little bit better idea of the slices in between, right? It doesn't mean you'll necessarily get a better plan. Now, absolutely, if it's a very distinct, many values, and the distribution is such that it would be really helpful to know that in this chunk, it's not just that it was higher, it's higher because of this one slice of values, then increasing it to something other than 200 might be really helpful. And I have tuned columns before, particularly in really heavy, really big, really transactionally heavy tables, because often, whether it's time series data, things like that, you get a lot of values and a lot of distribution. And so this can be anywhere from 100 from 1, which I don't know why you'd ever do that, to 10,000. So you could do 10,000 buckets for a column. Recognize it just means you're going to take longer as well. So the maintenance of it will be heavier because you're creating those buckets, but maybe it does actually always provide you a better plan for that kind of data without you having to do some other work. So it can be fun to play with it and see. And then again, you have the views that you can look at. So knowing what the statistics are is the place where all of this starts from, right? So the planner can't do anything unless it knows what it believes is available in the table. And then again, so generally automated, but you can trigger it manually through the analyze command. All right. So in SQL Server, we would say, if a query plan has been doing this kind of thing for a long time and suddenly it changes for no discernible reason and it got slower, generally the very first thing you tell everyone is, have you updated your statistics? And it could be, what normally happens is, because almost every database, it's a percentage-based operation. So after so many rows have been added or modified, analyze will happen to update statistics. Well, the larger a table gets, on a percentage basis, the more rows that have to be updated or modified before that thing kicks in. And so that's when you start to have the potential of, man, after a week, things seem to go wrong, and then I have to update statistics. Oh man, after another week and 3 days, it goes wrong. Probably that table might not be tuned well because it's getting too big and it's not updating things like statistics or vacuuming enough. So now that we have statistics, we actually want to see what the thing's doing. We have explain, which is essentially, we would call it an estimated plan in SQL Server. It's really just called the explain plan. This is what the server thinks it's going to do. It has done its cost analysis, and given the opportunity, this is the plan it's going to run. Explain analyze, which has nothing to do with analyze the command. Yet another thing that's really frustrating and annoying, but it is what it is what we would consider the actual runtime plan, right? So it's the good and the bad. It's going to take time. It does add some overhead because it's got to spit all that stuff out and collect all the statistics for you. And it is the actual plan. So you can analyze a delete statement. You can analyze an update statement. It will actually complete, right? So if you delete a row, you'll get the plan back, but the row's gone. So you've got to make sure explain will not run it, and maybe you just want to see, is the foreign key going to hit the thing, and it's going to loop, and so just be aware of that, and it's good. And then the last couple things, there are many, there's probably, I used to know the number, and I'm sorry it's not hitting me. There are, all these options, there are, I think, 11 or 12 of them now. These are probably, and then one more is probably the most used. So buffers is what adds to, again, a lot of these things for me, because I'm here, is from a SQL Server perspective. So we have this thing called stats.io that you can add in SQL Server. So that when you run a command, it will show you at the end every table and the actual amount of effort and work, the number of pages that were read for that table for part of this query. And so this is a really simple explanation. It doesn't matter what database server you're using. By adding buffers, we get to see how many pages that slice of the query needed to access to satisfy its part. And it's cumulative throughout the whole query, so then we can see in total how many pages of data needed to be accessed to satisfy this query? Well, what's the easiest way to speed up a query? To not do work. Like if you don't touch pages, that's a good thing, right? If somehow the thing could be satisfied by touching 1,000 pages, but you're constantly touching 1,000,000 pages, that's a lot of work. How big is every page generally in most database servers, including Postgres by default? 8K, right? So you do the math. And if you can reduce that, you have less I/O, generally. And then finally, verbose is used often. So the fourth one that I don't show here, which is often necessary for a number of tools that will help you with the query plans, is to do the output. So we have JSON, we have XML, we have some other things. So you can add that on as another option. And then particularly with JSON, a number of tools now use that because it's easier to parse with current technology. And so they'll use that to help you visualize a plan or do something like that. And I think that is it there that I want to talk about. So how is explain read? It is an inverted tree representation of your query, which means what's at the top is not where it starts. You find the thing that is furthest inward in the kind of pyramid of the tree, and that is where the operation starts, right? So it's from a inside out. And then it can be, if it's a parallel plan or there's multiple parts that can work in order, each of them might have their own starting point before they eventually merge together at some point later. There is no built-in visual explain plan, and there are many. So DPES is the most popular for sure. It's used just about everywhere. There is another one I don't have here called by a company. It's open source, Delibo. You've probably seen that one. It's honestly visually pretty nice. PG Mustard happens to be just someone that I got to know in the community. He's PGFM, the podcast. Michael Christophides, believe it or not, used to work at Redgate. And he saw years ago, he's like, Redgate's not doing anything in Postgres. I'm kind of annoyed with that. And I think there's an opportunity. So he left and created PG Mustard. And it's a query analyzer, query plan analyzer to try and help you. Does some machine learning, all kinds of stuff. He's just a great community member. It does have a fee, but I think it's like $95 a year for as many plans as you want to do. It's a really good tool, and I do still recommend it to a lot of people. So in SQL Server, what we would call nodes, or what we would call operators, is what nodes are. And so that literally, the first time I started working with, I was at Timescale, and I was working with the team, and I was talking to one of the head engineers for the Timescale stuff, who's contributed for a long time, about our planner, some of the stuff we were doing. I kept saying, so what about the operators? And he was like, why are you talking about operator? Like, I don't understand. It's like, oh, an operator is equal, greater than, less than, like that, because we literally can create our own operators in Postgres. He's like, do you mean nodes? I was like, okay, sure, whatever. So nodes are your things like your scans and your joins and what have you. Read from the inside out, and then generally, as data is pulled from disk, something's got to happen. It's got to be appended, it's got to be merged together, it's got to be aggregated, sorted, whatever, as you go higher up. So we've, again, probably seen this since everyone's mostly been working in Postgres. We have a plan, we have a join, and so in this case, we would say, right, these two, because they're the furthest inward, that's where this specific query starts. There's no other node, but I joined two tables, so it has to read data from both. One of them, it scans the table, and it filters out 75,000 rows, give or take. And then the other one, it does an index scan, so it knows everything it needs to. It's a small index. The biggest parts of what to read in an explain plan that will help you then do the query tuning. So the first one, this is why everybody I know recommends adding buffers, and there continues to be a drumbeat for many, many years that when we say explain analyze, buffers just happens by default, or at least make it a switch so you can turn it on so you don't have to add that second keyword, because it's really annoying. I don't know if you notice this, and I get why, but after you get past analyze, so there's two words that don't require buffers, parentheses, if you do them on their own. Analyze is the most popular. But as soon as I want to add another word, I have to add the parentheses. And it's really just stupid. I hate typing it over and over and over again, and I wish it would do it automatically. So we recommend buffers because it will tell you how many pages it had to read. And there are two big things. If it says shared, and there are a couple other little nuances, but generally shared and read. Shared means it was in memory buffers. So I did not have to get the page from disk before I could access it and do something for you. That's obviously going to be faster. And so we want, as much as possible, queries to access shared buffers. So we're looking for shared hits. It hit the cache, it hit the, the buffers hit in cache. The other possibility is read. So if you say read hit, it essentially means that it read the page from disk. So it was not in the buffer cache, and it had to first go retrieve it from disk, put it in buffer cache, and then it could access it. So obviously, if you have really high reads rather than hits, shared hits, then it's always going to disk. That's what we would call low cache hit ratio. The second thing is estimates, right? We've all heard of query plans where, again, the very beginning, first slide of statistics. It can only do as well in determining a plan as it has statistics to understand the data distribution. And so if it estimates a very drastically different set of rows than actually come out, it probably means your stats are out of date and you have a bad plan. So the way this works in Postgres is we have two sets of parentheses after every node. The first one that has the cost in it, that is what we would kind of say is like the estimated. We estimate that there's going to be 102 rows out of this query, right? This is a small query, but go with me here. And I'll get to the cost in just a minute. But actually, when I added explain and I ran this query, only 4 rows were returned. Now, this is a very small observation, but if this were reality, that's like a what? Math. It's like a 25x difference, which is really bad. That's definitely way beyond a magnitude of difference. And so we would say, hey, we probably need to update statistics here. There are a couple nuances that won't always get perfect, but you will get better. The next thing is the sort method or the hashing method. Essentially, it literally will say in the query plan, if you see the word external for any operation, that's analogous to a spill to disk in SQL Server. So we'll talk about it in just a minute. I'm going to show you an example in a demo. So anytime you have a slow query and you say, all right, I'm going to take the hit, do it again, and look at the explain plan, if you see external merge or external sort, it then gives you the amount of memory that was needed to do that sort. If it's in memory, great, it used that much memory. If it's on disk, then there's a calculation, and I'll show you how to kind of figure that out. And the goal is, if you can, obviously sorts, merges, hashes, those things are going to work a lot better if you can do them in memory, right? If I have to spit a hash table out to disk, actually you can't. Hash tables need to be in memory, but that's a bad thing, right? And then we continue on. Obviously, if you see that there's 3 scan types, right? And we talked about that actually on the next slide. But I put this here for a reason, so we'll talk about the next slide. Seek scans. So seek scan is analogous to a table scan. It's going to read every single page in the table. Now, there's a couple reasons that this can happen in Postgres, and this can be confusing. And I appreciated some new stuff I learned yesterday that I never had. I think Bruce had time to talk, and he just starts talking, and you're like, oh, I've never heard that before, and it was good. But from a scan, this is the one unique thing with Postgres that still sometimes messes with me. And it all comes down to this. Postgres is a heap-based database, right? So that means data is not stored in order on disk. So every page of data can have, let's say using time series data, the actual physical page on disk that's storing your rows might have data from 1999, and at some point later, there was enough space that it inserted a row from 2004. And so that can be all over the place. Like I point like this, that's a heap, right? There's no specific ordering. There's some ways over years we've made that better. Because it's random access, at some point, Postgres says, look, you have an index, but I'm pretty sure I'm going to have to read a lot of pages anyway because they're all over. It's literally going to be faster for me to read them, just read them in scan. It's no startup cost and filter stuff out. So often you'll get seek scans when you're like, I don't understand why. I have an index. Why isn't this working? And it usually means you can tune some other things to make that happen. We'll talk about that in a few minutes. And then the last thing I tell people to look for is honestly planning time. So generally you want sub-millisecond planning time if you can. 10 milliseconds is often pretty big, right? Depending on how complex the query is. All right, maybe 50 milliseconds because it's lots of tables and lots of data. But you get up to half a second, then something is happening here, and it usually means really outdated statistics. Maybe you're doing partitioning and there's lots and lots and lots of partitions. The biggest thing I see, because I've worked with a lot of partitioning stuff with timescale and others, is people end up, oh, I'm gonna partition this by week, or I'm gonna partition it by day, because that seems really cool. And all of a sudden they end up with 10,000 partitions, and they don't understand why when they do a date filter and something isn't materialized, it's planning all 10,000 partitions, which takes 2 or 3 seconds. Even half a second, like if that's happening every time you execute that query, that's significant. That is CPU being used every time. And so you need to do something else to lower that planning time. So it's great that you can see that. So let's talk briefly about cost. So the other two things that people often ask about, and it is actually really good to understand. All of these things are cumulative. Most of these things are cumulative, like buffers. I'll show you in a little bit. Actually, I meant to show you back here. Did I not show you that? I guess I didn't. Cost, so we have these nodes. You can see that these are the nodes that are happening first. And so the cost is the estimated cost for this operation. And again, it's all cost-based. So the one that hopefully was cheapest is the one that was chosen. And what this says is, this first one is a seek scan, could start immediately. It had no startup costs. So the first number we consider the startup cost, how long it's going to take before that operation can begin. And the second number is the total cost of this operation that it believes. Now again, cost is an arbitrary number, but it is within a query, it is relative, right? So if you have a node that has a cost of 10 billion and all the others are a couple thousand, something about that node, Postgres has calculated because it's something that it's going to be really, really expensive. But as you look up, notice that the nested loop has a startup cost of 0.28 because this one had a startup cost of 0.28. Like this could not begin, this one could not begin to loop until at least this index scan could be started. All right, so that's how they relate to each other. Same thing with time. So the actual time, in this case, yes, there's no cost to start the scan, but in reality, it took 0.05 milliseconds to get to the first file and start to open it, right? So the helpful thing here is you can actually identify, and it's not always where the most amount of buffers are read, a node that is taking a significant amount of time, right? You can actually find it and you can see, is it because something before it took time? Or is this the thing, this node for some reason is taking a lot of time and this is where I can focus my attention and my energy. Those two things make sense? It's pretty cool. You don't get that in all the others. Like I can't get the startup cost in SQL Server to understand why that node is doing that. Actually, I don't even think I can get the estimated cost, the cost at runtime to figure out why it chose that specific node. All right, so now the primary scan node. So we can see an explain plan. We understand statistics are how all these things happen, and we only have 3 basic node types for getting data off disk. One is seek scan, read all the pages. Now, it obviously is generally higher I/O, right? If I have to open every page, that's not a great thing, but it might actually be better for this specific data type or because of the amount of rows I have to get to anyway. An index is simply pointing to many, many pages. Index scan is a good thing, right? Using an index is good, but it also means that an index scan actually will be disfavored often, more often than you would think, because it's actually a double operation. First, you have to open up the index, identify the pages of data that we need to go get, and then we need to go get those pages, and because we're heap-based, that is random access, and that's more costly. And so, there's this fine, it's not defined, it is a cost-based setting, but when the cost is estimated to be too high for an index scan, it might flip over to seek scan. It's like, well, why would I take the startup cost and then still have to go do all this stuff? And the other thing that's interesting about an index scan, I learned yesterday, and I didn't realize this, one of the other reasons that it can favor seek scans is an index can point to the same page multiple times over and over again, right? And so technically, it's accessing that page over and over and over again, even though it really only had access at one time. And so you'll see instead of an index scan, you might see more of a bitmap scan. We see that much more often than an index scan. Because the reality is it's saying, I'm just going to bitmap, I'm going to find all the pages that are repeated, and then I can just go access them one time. I don't have to like, oh wait, I was here. Oh wait, I just opened that up again, I was here. Oh wait, I was here. Because you might access it at the beginning of the index, and you're scanning through, and then you realize, oh, I need to go get that page. Wait, I already opened that page. So that was interesting. I didn't realize that. Then index-only scan is great. It just simply means everything you need from that table is available in the index already. Indexes are generally much smaller. Of course, we'd rather that because we don't have to go access the heap. Indexes are ordered, right? So it helps in getting things out. And then the three major join types we have. And again, this is what's so interesting to me. Like this is it. There's not a lot of other things. Unless you get, different flavors of Postgres have added their own node types, even though they're based on this. So a quick example, even for the scan, is timescale has compression. And so it is a scanning node, but it first decompresses the data as it scans it off the table. And so you'll see it as a different node type, even though essentially it is a scanning type, but it has to do some extra work. But in Postgres, this is it. So nested loop, obviously it's a row-by-row operation. We have two tables, and we have no other way to determine that I'm looking for a join from this table and this value into all the possibilities in this table over here. And I do it row by row by row. It's hopefully only chosen if one of the sides is relatively small. If there's no other option and a nested loop is still the one it has to choose, and there's lots of rows, that's when we get a slow query, because that's to scan a lot of rows, row by row by row on each side. Hash join is often chosen when you have relatively larger tables that hopefully the hash table can fit in memory. And so one side of the join would be hashed first. That way, then the outer table, even if it's larger, can probe into that hash table to identify the pages that can be joined where the data's at. And then finally, you have merge join, which is really efficient generally, but it can only be used when all the data on both sides of the join is sorted, right? Because it can just identify, I'm going to start here, can I read one from here to insert as I spit out the output or not? So it's very efficient. And then we have lots of other working kind of nodes, right? So once we get the data, once we've identified how to join it together, there's dozens of these things, aggregates and sorts and groups and group aggregates and all kinds of things. And so that's what you'll see in the query planner. All right, I'm going to go through these next couple things and I'll give you a demo. I'm going to breeze through this. Who has used pgstat statements, knows what pgstat statements is? Okay, let's go through quickly then. So pgstat statement. This question, I've gotten this so many times, even just this week. And we talked about it at dinner last night. I went to dinner with a bunch of the folks just to catch up. And why doesn't Postgres, by default, why do I have to turn something on to get metrics about my query as it's running? That happens in all the others, right? Does anyone know why we don't turn this stuff on by default? It could be costly. Doesn't mean that it is, but it could be. And so the project says, we're not going to make that choice for you. We're going to give you the switch, but we are not going to force you to take the extra hit of getting the statistics. That's how a lot of these things are developed. It's there, but you need to decide and make the choice. Now, the reality is, I don't know anybody that doesn't turn this on, shouldn't turn it on. The actual overhead of pgstat statements generally is very minimal compared to the value that you get from it. Every hosting provider, it is available. You just have to actually go in and turn it on. You do it through a switch called shared preload libraries, preload shared libraries. But it's easy to do. And once you do that, every database in the cluster, every query that's run is logged to this internal table. By default, The target, I think it will store up to 5,000 queries. You can adjust that. There's all kinds of ways you can adjust PG-stat statements. But just out of the gate, it will start logging the query text, things like how many rows are read, how often was this query called. I'll show you this rows in just a second. And the problem here, though, yeah? Interesting. I wouldn't have thought about it that way. The difference is query store actually also tracks the query plan. PG-stat statement does not track the query plan. This is simply query text parameterized, right? So it's not the actual where values, the predicates are not stored. It's parameterized. 100%. Number of executions, all that stuff. You can hone in on the things that maybe you're going to need to tune for sure. There are ways then to store the query plans with, again, another extension. The thing that is you can't answer with this, though, it's cumulative, right? Until that value is reset, and you can reset statistics to 0, as long as it's keeping statistics, it's just cumulative. So I can never answer this question. I can see that a query has been run 1 billion times, but I don't know if that's running 1 billion times just because that's what it needs to do, or there's something really inefficient about that, and running 1 billion times is kind of like death by 1,000 cuts, right? So 1,000 times, sorry. You can't do that because it's cumulative. I can't say like, oh no, I'm having a problem. Look at PG-stat statements table, select star from PG-stat statements, and quickly identify the problem query. You just can't do it. It's not possible unless you can get deltas around how this is running. There are lots of columns in PG-stat statements. I don't know why I'm standing out here because I hate looking backwards, but I just don't like being trapped back here, to be honest with you, but I'll do this because I don't want to keep looking backwards at you. So lots of different, execution time, all these things, total, min, max, mean, standard deviation, how many calls, how many rows have been pulled for this query. Same thing with buffers. How many buffers have been pulled if you turn that stuff on? Wall, all of this stuff. As of PG-16, there were 43 columns that were stored as could be stored as PG-stat statements. If you asked it to track I/O, even those things would be there. You can turn some of those things on and off. Here's some. This is not all 43, but you can quickly see things like, again, I guess I don't know what this was from that I pulled it, but so I have zeros here because by default planning time is not tracked. You have to turn that on because that adds additional overhead, right? I/O is not, like actual disk I/O is not tracked by default because that adds additional overheads. You can turn that on. But you can see that the total execution time for 151 calls is 8 milliseconds, 8.4 milliseconds, right? So as we go, 1,000 calls, 10,000 calls, that number would go up. Then it has the min, the deviation, the standard deviation, the mean, and so forth. And then the other thing that's happened since Postgres 14, I think it is. There's always been a query ID, but it couldn't be correlated with other things like logs because it was generated as an internal Postgres piece that extensions didn't have access to. And that was finally changed in Postgres 14, where it's a shared module now that allows you to, it can now be shared among all the pieces. So if I do log my execution plan, I can actually see which query specifically this execution plan is for because the query IDs will now match. And hopefully you're using a tool to help you do that, and it will make it a lot easier. As I said, all statistics are cumulative, restart or until the reset. Now the nice thing is, Postgres 15 added, or is it 16? 15 or 16 added a predefined role now that allows non-super users to reset statistics. So in the old days, the only way you could do this was I'm having a problem right now, the fire alarm's going off, I reset my statistics, I wait a minute, and I query PG-stat statements again, and I see, oh, this query is doing a lot of work, I'm gonna start there. But that's not really an effective way to do analysis, right? Or forensics. I knew the word would come, forensics. So You do need a tool. Yeah, I work for Reggae, so I'm going to put this up there because I really like it and I think it's doing a good job. But any tool you can find, if you can do it yourself, you can write a cron job that samples pgstat statements every 5 seconds, 10 seconds, 1 minute. And then you just log those cumulative values and then do deltas, right? So as long as you have a timestamp, you can see when that one query was taking a lot of effort, right? So you can do it, or you can get a tool that will do it for you. But if you do track it, this is not the actual values. These are the deltas between the two samples, right? So you can see how much time this query was taking, and then, oh, something happened here. What was that? And what is that? That is execution. So all of a sudden, a bunch of execution started, and now it went up, right? So you need to be able to identify this. It doesn't come out of the box. You do need to do something. There are some open source opportunities for this. Many of your paid solutions will provide it as well. But you can only do it if you're storing the data. There's no other way to do this. You have to have something to store these samples. And then finally, one of the things that's great about pgstat statements is you can begin, and pgstat IO, table IO, is that you can start to identify things like cache hit ratio. So for every query, how many reads came out of the buffer and how many came off of disk? And you say, oh, that query is really slow because it seems to be doing a lot more work, or at least right now, more work off of disk. All right, so we can see the plans. We can start to see some statistics about the plans. But then what do we do about it? How do we actually improve the server? What are some tips to get started? The description of this thing was a beginner's guide. And so what are some of the things that you may or may not know about that can actually impact your queries on the fly? And then we'll talk about a couple ways to do it as you go. There are over 300 configuration options in Postgres. And we're going to talk about every single one of them in 5 minutes. Buckle in! All right. No, we're going to talk about 3 or 4 that are actually, I think, 5 or 6 I think are really important. I've been saying this for years, as long as I've been back in Postgres and I started to learn this stuff. Every single Postgres instance, aside from most serverless things, does still need to be, wow, we are really going to truck along here, it's going to be awesome, does need to be tuned. All right, that's all there is to it. So either they give you a UI for it, or you do it yourself in PostgreSQL.conf. This is how you see what your current settings are, show, and then the parameter name. Show all will spit out an enormous table that you'll be confused by, and you probably don't need to know like 90% of it, 95% of it. These are the ones that matter most. Number 1 is shared buffers. Over and over again, particularly those newer to Postgres, assume, well, I spun up an RDS instance. Why do I need to do this stuff? Well, RDS will give you, hopefully, a sane value to start based on the resources of the server you're renting from them, but they don't know your workload, right? It will probably, I think their formula ends up being close to 25% of total RAM. Maybe you need more. Maybe it worked better for you at 30 or 35%. Or once you get to 30 or 35% of total memory and it's still not working, it probably means you need to buy up and get more actual memory and resources. But you need to look at your shared buffers. By default, shared buffers is 128 megabyte. I'm guessing you have more than 128 meg in your database. I could be wrong. But if it can't fit in memory, there's always this contention. You're pulling and pushing pages over and over and over again to satisfy every query. Workmem is the amount of memory on the worker nodes in your query. So those nodes that do hashing, sorting, grouping, hashing, merge joins, things like that. The node itself can use up to this amount of memory. And so if the chunk of data it needs to aggregate or build a hash table on cannot fit in that memory, it will have to go to disk. And that makes things really slow. And over again, the only way you can tell this is to look at the execution plan and see if something is happening external on disk. So the problem here is you can change this for the entire server. You can set minimum work mem to 8 meg or 16 meg. It's 4 by default. But then you have to recognize that every single node, if there are 100 queries happening right now, and all of them have 3 sorting operations going on, they can all use That's 300 operations can all use up to this amount of memory. And if you're not careful, you're going to start to run out of memory on your server pretty quickly. So you have it's kind of this balance, right? You probably need more than 4 for most modern workloads, but it shouldn't be 32 meg by default or 64. You'll probably get by with 8 in most work cases. In some cases, if they have 128 gig of RAM or something, I might say, yeah, make it 16 meg to start, because you have plenty of RAM and you're controlling your connections with buffer pools and, not buffer pools, with a load balancer, things like that. So there you go, blah, blah, blah. Really, cache hit ratio is about the only way you can identify if this is even close. If your cache hit ratio is at 50% consistently, you're like, just go home, right? Or you have to spend more money. Something has to happen. You need more RAM. If it's always pushing and pulling data out. Generally, anything less than 90% consistently is like, yeah, you really need to look at this. Can you simply increase it a little bit on your server? Maybe it's just not set well, and it's okay if it goes to 30% of your memory or 35%. Great. If you go to 30 or 35 and it still is at 70%, you just need a bigger server. You need more RAM. There's no other way around it aside from purging data, tuning your stuff. And then this is a general query that is helpful. There's a couple ways to get cache hit ratio. pgstats.io table is a pretty efficient way to do it. Workmem, I've already said. I want to show you a quick demo. Right, 4 meg by default, 816. And then this is the last point I want to show you. A lot of people don't know you can do this. You can set it on your session. This is most helpful when you know there's that one query that's always taking a long time. You eventually do the query plan, and you realize, all kinds of data is being spilled to disk to do this sort. And if you just could increase it to 128 meg for that query, hey, it would run a lot faster. So you can set it on the session. I don't recommend doing it for every query. This is most helpful for things like nightly jobs, right? You have a nightly reporting job, and you know it's going to be slow, and no one else is using the database at that time, so go ahead and make it 512 meg, and that query runs really fast, and then you move on with your life. The other couple, I'm not going to spend a lot of time on. I'll make sure these slides get out there at some point and talk about some of this. So maintenance workmem is mostly, it can impact your queries because it's keeping the stuff up to date that it needs to, but let's move on from there. These are the last two that I think most people don't know about, and it's getting more airtime now, but random page cost, we can configure. And so again, we have lots of random I/O, but modern disks being SSD, random does not matter nearly as much anymore. But it is still set to 4 by default. Just like everything else, the core team is not going to change that for you because they don't know your hardware. And so you can change it. And the general recommendation at this point is almost everywhere, including EBS volumes. AWS actually says this. Set it to 1.1. It's slightly more expensive than sequential scans because, again, sequential scan is going to be the fastest thing you can do. So absolutely change that. Honestly, if you haven't, go home and change it. Maybe you'll need to increase it a little bit. Never make it less than sequential scans. That makes no sense. But you should change it down to 1.1, 1.5 something and see if some of your queries actually get better plans now. And then last is effective cache size. If this doesn't get changed, this is simply used for planning. This does not actually take any RAM on your server. It simply is saying, hey, Postgres, shared buffers is 25 gig, and the computer itself has a fair amount of space for caching data itself on disk and other places. And so, by the time you actually have to go to disk, it's quite a while, right? There's a lot of space. And so you can set the effective cache size. Generally, 50% is a good recommendation to start with of total memory. And the cool thing with this, just as a hint, if you ever have a smaller server for testing, but you can get like a backup of your production data or something close that is close to it, you can run that same query if you set the effective cache size to the same as your production server, because it's not actually it's not using this memory, but the planner is more likely to choose a similar plan to what it is on production so that you can begin to tune it. Kind of cool, right? A lot of people don't know that. Statistics target, I'm not going to go through. I just want to show you. I will say this, extended statistics was brought around in Postgres 12, I think, or 13. I don't remember which. And this is actually a really interesting way. If you really do have like a really big data table, and you know, the planner has no idea. Remember, statistics are taken on every single column, but it has no idea if column A and B are actually related. Every time I query ID this, I'm always going to get 10 values, right, for that time. If you know there's that correlation, you can now create an extended statistic that will actually understand the correlation. So now it can make a better estimate on how many rows are going to come out when you filter on those two things. Kind of cool, right? I just want to really, I mean, technically we're at time, but let me just show you a couple things. Other things I was going to talk about, that was mostly it for the beginning stuff. Let me show you quickly the impact of a couple of these things. It's not a huge database. I have, I don't know, 2 million rows in this one table. Here's my good old explain plan. The biggest thing here is, you'll notice, this is really why I'm showing it, is it's all cumulative, right? So here's hit in red, and then you see 1837 is on the next node up here, but hit is 174 because down here is 1724, right? So you can see that they're added as they go up. So at the very top, all of these operations, there were 9,170 pages in cache that it could read, but it had to pull out 3,500 pages from disk to read. It was not in cache, right? That's because I don't have a lot of, and if I run this over and over again, eventually you see like, oh, okay, well, this query can fit in disk. It's gotten all the pages in memory, and now it can just pull them out. It becomes much faster. But if you keep track of that on a real server, it's probably not going to happen. A more complex query, however, that has to pull from multiple tables, you'll see that it's reading lots of pages from disk. So there's two things I can fix here that, as long as you can see your plans, a lot of people don't know can happen. One is, it's pretty evident I don't have a lot of memory for this thing to be storing pages in cache. It doesn't matter how many times I run this, I'm still getting very similar. They can't fit anything more. Something's not good about that. And then the other thing is, you'll notice it doesn't have enough memory to do this this sort in memory. So it has to spill to the external disk, and it needs about 2 megabyte of, maybe 3 megabyte of space on disk to satisfy this query. Well, the reality is, I have 4 megabyte of work mem. It needed essentially an additional 3. And so for this one operation, I probably need somewhere between 8 and 10 meg for that work mem setting for this thing not to spill to disk. The other thing here, it's actually, I'll show you in a second, it ends up being almost 20 because it is the, which one? Also, I believe it's the hashing. There's this, what's that? Parallel. Well, it is parallel. That is part of it. But parallel individually doesn't impact this. It's actually the hashing that they assume they actually internally give it twice the memory. Because again, a hash table has to be in memory. And so in reality, it's not just 7 because there's hashing things going on here. It ends up being close to twice as much. Right, so let me just show you these two things, then we'll call it a day and go from there. So if I set the work, I'm in a session, I'm connected. If I set the work mem, and I'll start with 10, and I think we're not going to see the external. Oh, we did. Okay, so that one had an external. That was enough. If you work your way down, it was 4, or maybe I had it set as something else. If I go to 6. That's still enough. Okay, well, you know what? Maybe down here. Somewhere there's still an external when I was running this previously, but on my, well, how's that for a demo, huh? Anyway, obviously if I reset it to 4, which is where it was, I don't get it. And we're back to an external sort. Oh, you know what? I removed rows from this table for another example. I forgot that. I've been using this demo database for the last couple of days. It doesn't have 5 million rows like I was used to. Oops, that's why the settings aren't working like I expected. Okay. But then the other thing is share buffers, right? So we said this complex query is reading from lots of tables. 2 of them have a couple million rows. And so I didn't set the defaults. So I could do it in the PostgreSQL conf. I can actually alter the system if I'm a super user. And so this actually writes it to the conf. And then I just have to restart the server. It only can be changed at start. You can't reload, so the server actually does have to be restarted. So now I can see that I have a gig. And if you remember before when I ran this query, lots of data was being read from disks. So initially it looks like, well, shoot, that didn't help. But that was a first read. As soon as I do this, oops, come up here, you'll notice now all of that fit in shared buffers. And so this query is effectively, I didn't show you before, but it essentially sped it up by 2x, right? And then it still is doing the external sort. So I'm guessing if we do, let's just do 10 again, that was what? I think it was about 600 milliseconds. Is that where we were at? And we've come down a little bit more, come down maybe 25% by giving enough RAM. So just a couple of those things to go. I was going to talk about indexes next, the various types of indexes, which can be really essential to tuning your query. And I'll just have to keep reworking this talk a little bit to make sure I can hit it all. Sound good? Come chat, come talk. I love talking about this stuff. And hope you guys are having a good time at Past Summit.